Hello ladies and gentlemen, this is Mr. Cunningham, and what we're going to be talking about today is acids and bases. So go ahead and try those bell work questions that are on the video, then we'll start talking about our objectives. So now that you've had a chance to go through the bell work, let's talk about the objectives that we're going to have today. So sub-objective 1 says that we need to be able to describe properties of acids and bases. Sub-objective 2, explain the Arrhenius definitions for acids and bases. And then our goal, to understand acid and base strength depends on its ability to ionize or break apart in solution and draw a particle diagram of it. So here we go. Here's some properties of acids and bases we're going to talk about. So acids, probably the biggest property, the thing that you guys need to have memorized, is acids produce H plus ions in solution. We also can call that H3O plus. I will kind of use those two things interchangeably throughout this entire unit. If I say H plus, I mean H3O plus. If I say H3O plus, I mean H plus. So H plus is just called a hydrogen ion. H3O plus is called hydronium ions. But really they kind of mean the same thing. They have a sour taste. They corrode metals. Oftentimes when you see batteries like on the inside of like an old electronic thing, you'll see the batteries are all nasty on the ends. That's from some battery acid that's probably leaked out. They're good electrolytes, which means they conduct electricity. They react with bases to form salts and water. We'll talk about that later on in this unit. And their pH is less than 7. Okay, so those are some properties of acids. They also turn blue litmus paper red. Here are some common acids that you guys might have heard of. Acetic acid, which we've used a lot in our labs, is also known as vinegar. Like, vinegar is a solution of acetic acid and water. Then we've got hydrochloric acid, that's in your stomach acid actually. Then you've probably heard of citric acid, that's used in fruits. Carbonic acid is in soft drinks, as well as phosphoric acid. So those are kind of some common acids that you have probably come in contact with, really you come in contact with on a daily basis. Here are some properties of bases. Bases generally produce OH minus ions in solution. They taste bitter or chalky. They're also good electrolytes. They feel soapy or slippery. They react with acids to form salts and water. Their pHs are greater than 7, and they turn red litmus paper blue, meaning it is a base. Here are some common bases. You guys have probably maybe heard of a few of these. Sodium hydroxide is known as lye. Potassium hydroxide is used in liquid soaps. Barium hydroxide is a stabilizer for plastics. Magnesium hydroxide is used in milk of magnesia. And then aluminum hydroxide, which is used in antacid. A lot of bases are used as antacids. Now here is kind of our next objective, which is over the Arrhenius definitions of acids and bases. So here are the definitions of what an acid is according to the Arrhenius definition, which is an acid is a substance or substances in water that increase the concentration of hydrogen ions. The base definition is substances in water that increase the concentration of hydroxide ions. So the good thing about this definition is it's really easy to sort substances into acids and bases. Here's basically all it is. We'll look at this too a little bit later. If you see hydrogen at the front of a compound, it's an acid. If you see OH at the end of a compound, almost always it's a base. So the acids and bases are really easy to identify using this definition. So something like some examples of Arrhenius acids and bases, I look at H2CO3, okay, that's carbonic acid. I know it's an acid, okay, I would define it as being an acid because I see that H plus at the front, or I guess you don't see the H plus, you see the hydrogen, but really that is H plus. It would produce hydronium ions in solution, so I would categorize it as an acid. For this one, this LiOH is called lithium hydroxide. That would be a base because it contains OH minus. Remember, that's the polyatomic ion that's called hydroxide. So if you see a compound that has hydroxide in it, or OH, it's a base. If you see a compound that has just hydrogen almost always in the front of the compound by itself, then that will be an acid. Now, what's really interesting is water, you might be like, water is H2O. Well, we can actually, it's sometimes also written as HOH. You'll notice that it contains hydrogen in front, just like this acid. It also contains hydroxide in the back, just like a base. Water can actually act as both an acid and a base. So when we start talking about neutralizations, which will come up in a few lessons, we'll be talking about how water works into those reactions. So next thing we're going to start talking about is kind of our goal for today, which is to be able to look at acid and base strength. So how we define the strength of an acid and the strength of a base is on its ability to ionize. What ionize means is break apart, okay? So strong acids transfers all of its protons to water and it completely breaks apart, okay? So things that are strong acids, their molecules break apart, which means they, some words we would typically use for that is they completely dissociate. Okay, so to associate, or an association, is a coming together of stuff. To dissociate is to break apart. Okay, so completely dissociating is what strong acids do. All right, they're also very strong electrolytes because they separate. Weak acids, on the other hand, they only transfer a part of their hydrogens. They only partly ionize, which means they only partially break apart, and they are weak electrolytes. Okay, so they do not conduct electricity very well. They do a little bit, but not a lot. Okay, so here are a list of some strong acids that you guys need to know. There's hydrochloric acid, which is HCl, nitric acid, HNO3, sulfuric acid, which is H2SO4. Sulfuric acid actually has 2 hydrogens. So again, notice how every one of these compounds has H in front. That's how we can identify them as being acids. Then I know they're strong acids because they're on this list. These, when I say these things are strong acids, it means they completely dissociate. Any other acid that you see is not a strong acid. So we are only going to really split these apart into 2 categories. We've got all the acids that we could ever have, and they all have H in front. Then of all of those acids, there's some that are strong and there's some that are weak. There are 6 of them that are strong. That is these. I want you guys to know these. Then, if you see any other acid, we consider it to be a weak acid. So, how do we represent this? How does it look between a strong and a weak acid in solution? So if I was to draw something called a particle diagram. So on the back of your notes page, I want you guys to draw this. So, and again, as you're drawing, please listen to what I'm saying because it's important. So strong acids completely dissociate in solution. Weak acids only partially dissociate. So let's pretend for a second that each one of these red dots represented our hydrogens. So let's go back, let's pick a strong acid. Let's say it's HCl. Okay? Let's say that this over here is our strong acid. So each one of these red dots would represent hydrogen. So each one of these red dots would be an H plus ion. Then these other blue things would be the anion. Remember, every acid is going to have a cation, which is the H plus. Then it's going to have the anion, which in this case is chloride. So that means all of these blue circles would be Cl minus. So on your drawing, I want you to draw these red dots kind of as H plus, and these blue dots as Cl minus. Okay, that's what it would look like. Sorry, on your notes page it says to draw HNO3. So you would draw your hydrogens, your H pluses, as separate. Then you would draw NO3 minuses as kind of like these blue dots. Weak acids do not do that. They only partially dissociate or partially ionize, which means notice how most of these are together. Okay, so undissociated means they're still together. So on the right side of your notes page, it says to draw a particle diagram of HF. Well, HF hydrofluoric acid is not one of these 6 strong acids, which means it's a weak acid. That means it's going to look like this in solution. So, how I want you to draw this particle diagram is, these red and blue circles that are still paired up, that represents a molecule of HF, hydrogen and fluorine still together. But some of them break apart. So these 4 will be H and F together. These 4 right here. But then these other particles right here, this red one would be an H+, this red one would be an H+, this blue one now would be our F-. So some of them have broken apart and some of them have stayed together. Strong acids completely dissociate, they break apart into their H+, and then the anion. Weak acids do not do that, only some of them break apart. Okay? So now let's look at base strength. Okay? Bases, or how strong a base is defined the exact same way as an acid. Strong bases are molecules, all of the molecules will accept a proton. They completely dissociate, which means they completely break apart. They are strong electrolytes. Weak bases, only a fraction of the molecules accept protons. They only partially break apart or partially ionize, and they are weak electrolytes. So, back to our particle diagram. Let's look at the list. Here are 5 strong bases that I want you guys to memorize, okay? Again, if you see these bases, if you see LiOH, NaOH, KOH, BaOH2, barium hydroxide, or calcium hydroxide, automatically assume strong base. Now, here's what that means. If we were going to draw a particle diagram of them, okay? Again, they're going to look just like the acids would look. Okay? The only difference is instead of an H+ and then our anions, now it's going to be a cation and our OH-. So let's pretend, let's see, on yours, it says that you need to draw a particle diagram of beryllium hydroxide. Okay? Well, is beryllium hydroxide one of those strong bases? Let's go back and look. It is not. There's barium hydroxide, not beryllium, which means beryllium hydroxide is a weak base, which means it's going to look something like this. Okay? Now, beryllium hydroxide has 2 hydroxides for every 1 Be, which means if I had 1 beryllium atom, it would have 2 hydroxides. So whenever you're drawing your particle diagrams, it's going to look something like this. So here's what our beryllium hydroxide would look like. So you've got your water line here. What we're going to have is, because beryllium hydroxide is BeOH2, that means I have 1 beryllium and 2 hydroxides. So when I draw its particle diagram, I'm going to have, I'll just let my brown represent Be. Okay, so I've got 1 Be, and then I have 2 hydroxides connected to it. And then if I draw another Be, it's going to have 2 hydroxides connected to it. Now remember, this is a weak base. So that means it only partially dissociates. Okay? Now I could also draw it maybe something like this, you know. If you're sick of drawing like the Be's, you could just draw like a brown circle and then 2 green circles for the hydroxides. Okay? So we're going to have a bunch of molecules that look something like that. Okay, so I'm going to have 2 hydroxides and a beryllium. Now, some of the beryllium hydroxide does dissociate. Now, I'm only going to draw maybe 1 or 2 of these, which means some of these things do break apart because it is a weak base. So what I would draw is I would draw maybe 1 particle, that's my beryllium, but now that's Be plus 2, and then I've got OH minus floating around in here. Now if you were going to draw it using the symbols, then you'd write like I've got Be plus 2, and then I've got OH minus and OH minus. So if I was going to draw this acid, or excuse me, this base with this, like with my symbols, then I would draw maybe something kind of like this. So I'd have most of my particles are going to be Be with 2 hydroxides connected. But some of them, maybe 1 or 2 of them, will be broken up like this. And because I'm going to have 2 hydroxides for every 1 beryllium, because in the formula, every time I have 1 beryllium, that means I need 2 hydroxides. So now let's look at our other one, which is sodium hydroxide. Is sodium hydroxide a strong base? Let's go back and look. Yes, it is. Sodium hydroxide is a strong base, which means its particle diagram is going to look like this. Okay, you're going to have sodiums, and you're going to have hydroxides, and they're all going to break apart. So let one of these particles represent kind of your sodium, so write like Na plus. Then let another particle represent your OH minus. They're all going to be separated. Okay? So that ends our lesson going over acid and base properties. Hopefully you found the video helpful. If you have any questions for me, make sure you let me know. Thanks for watching.